Hi, grade 11 and 12s. We are still working through the KA and KB package. We're on the fourth page of that package. It looks something like this. So we learned how to calculate the concentration of ions. We want to know how much H plus or how much OH is in something. So we learned how to do it if it was a strong acid or a strong base. Now what we're looking at is if it's a weak base or a weak acid. And there's these three steps that we're always going to follow. Write the balanced equation. We're going to look up Ka or Kb, and that's found in your table 13. And then we're going to set up the equilibrium constant expression. Okay? Remember again that a weak base or weak acid means that not everything is ionized. In a strong acid, you put HCl in, you get a bunch of H ions and a bunch of Cl ions. In a weak acid, only a little bit of it actually ionizes and changes into ions. So we finished this first example, and now we are going to work on example 2. It says calculate the hydroxide ion concentration in a 0.025 molar solution of aniline, which is a weak base. So right away they told us it was a weak base, so we need to follow these three steps. First step is a balanced equation. Okay, so a balanced equation for this is going to be C6H5NH2. Okay, and this said it was a base. So what's going to happen is I'm going to have OH ions. So in order to do that, I need water. Okay, and this is just what I'm teaching you. You guys don't know this yet. Okay, and that, because it's a weak base, we could actually say it's in equilibrium. You're allowed to do that with weak base because it's not completely ionized. It becomes a little bit ionized, and then there's some turning back into. Don't worry too much about that either. But this could be a clue that it's a weak basis if you have that symbol. And we actually should have put that symbol back here. So take a sec to do that. So weak bases are in equilibrium. Okay, this is going to break down into our OH. So it's like we've lost one H there, and then we're going to gain one H over here. So hydroxide ions plus C6H5NH3. And that's going to have a positive charge. These are both aqueous. Okay? So now we do this. Now we look up the Ka or the Kb. And you're going to look up Kb for this. I'll give it to you right here. It's 4.3 times 10 to the minus 10. Okay? This is also going to be equal, the equilibrium constant. This is going to equal the OH ions times the concentration of the C6H5NH3 ions. We're not going to include water because it's liquid, but we are going to include C6H5NH2. Okay, no squares because this was balanced as it was. We had the same amount on each side. Okay, the concentration, or the problem tells us the concentration of this is 0.2025 moles per liter. And we know from mole ratios that these two are going to be the same. They're not going to be the same as this guy because it is a weak acid. It doesn't completely ionize, but they are going to be the same as one another. Okay, so now we just sub in what we know. We know 4.3 times 10 to the minus 10 is equal to X, which is the concentration of OH, times X. I could also just write that as X squared over 0.025 moles per liter. Okay, what we're going to do is we're going to solve for x squared. X squared is equal to 0.025 times 4.3 times 10 to the minus 10. Square rooting, I want you to press pause on this, and I want each of you to get out your calculator and see that you can get this answer. Okay, your final answer should be 3.3 times 10 to the minus 6. And this is what? This is a concentration. We are finding the concentration of OH ions. Concentration is in moles per liter. Okay, if you did not get this answer with your calculator, I want you to find someone in this room who could get this answer and get them to do the calculation with you. A lot of times brackets will help and making sure you enter correctly. Okay, moving on to the next page. Finding OH ions in acids and H plus ions in bases. When we need to determine the ion concentrations of an acid, you should immediately realize you will be finding the concentration of hydrogen ion and some anion. So an anion, remember, is a negative ion. So we saw chlorine and we saw C2H3O negative in the other one. The concentration of the anion normally doesn't concern us much. When finding ion concentration of bases, we determine the concentration of the hydroxide ions and some cation, so some positive ion, such as Ba2 plus or C6H5NH3 in our base examples above. Again, we aren't too concerned about the cation concentrations, but remember water. Remember water, we found that its Kw was equal to the concentration of H ions times the concentration of OH ions. And we found that this was 1.0 times 10 to the minus 14. We did this work at the beginning of yesterday's class. Okay, so when we didn't include this guy because he's liquid. When we make an acid solution, the hydrogen ion concentration will increase because we are adding more H ions to those already present in water. Consider our strong acid example, and that was HCl, was our strong acid example. And we found the H ions was 0.05 moles per liter. If we add this to the hydrogen ion concentration of pure water, 1.0 times 10 to the minus 7, we get a total concentration of 0.050001. So what they did is they said, well, what is 0.05 plus 1.0 times 10 to the negative 7? Well, that's 1, 2, 3, 4, 5, 6, 7. And they added those together, and this is what they got. Okay, clearly water adds little to the total and we can essentially ignore it. Next, remember that equilibrium constants are a constant as long as temperature does not change. Thus, the value of Kw will still have a value of 1.0 times 10 to the minus 14 even though hydrogen ions has increased due to the presence of the acid. We can use this information to calculate the concentration of hydroxide ions present in the aqueous solution. Okay, and that's what we're going to do right here. So we know that Kw is equal to the concentration of H ions times the concentration of OH ions. Okay, and we saw in the last example that this example back here, we found the OH ions, the concentration of the OH ions to be, sorry, we're not back at this example. We're still looking at HCl. I got ahead of myself. At the HCl example here, we found that the hydrogen ions had a concentration of 0.05 right there. So we could solve this for OH. And that would be, if we solve for OH, it would be Kw divided by H. Subbing in the values that we know, Kw we said for water was 1.0 times 10 to the minus 14. We found that the concentration of H in HCl was 0.05. Okay, so I'm just going to make a note here from HCl example. So we could find the amount of OH in an aqueous solution of HCl. That's what we're finding right now. All we have to do is divide these two things. Putting them in our calculator, we get 2.0 times 10 to the minus 13 moles per liter. So not a whole lot of OHs in HCl, which makes sense. It is a strong acid. Okay? Moving on to the last page. Le Chatelier's principle. Remember Le Chatelier's principle? When we disrupt an equilibrium system by increasing the concentration of a reaction participant, the equilibrium will shift to minimize the stress. When we increase the H ion concentration in the water equilibrium system, the reaction will shift to the left to use up the additional H. This will cause the concentration of OH to decrease. Indeed, we saw that OH does decrease from original concentration of 1.0 times 10 to the minus 7 in pure water to 2.0 times 10 to the minus 13 in our acid solution. So that's what we saw here. Normally, we had each of these concentrations were the same, and they were each 1.0 times 10 to the minus 7. But when we added HCl, we saw that it now the OH concentration was 2.0 times 10 to the minus 13. And Le Chatelier principle shows that because we had H2O go to H plus OH. So if we add a bunch of this, it's going to shift this way and use up the OH. We're going to have less of it. Okay, we can apply the same calculations to determine the hydrogen ion concentration in any basic solution. Let's return to our weak base aniline example. Okay, we determined that in a 0.025 molar solution of aniline, C6H5NH2, the OH was, what did we find it to be? We found it to be concentration of OH. Looking back in our notes, we found it to be the concentration of OH to be 3.3 times 10 to the minus 6. Our new question, what is the H concentration in this basic solution? To solve, we once again refer to our pure water equilibrium and its equilibrium constant expression. This time, however, we have determined OH and need to find H. So again, we say that Kw is equal to H times OH. And in our example, we said that OH, this guy, was 3.3 times 10 to the negative 6. And Kw is always a constant, and it is 1.0 times 10 to the minus 14. I want you to solve for H. You should get 3.3 times 10, oops. You should get 1.0 times 10 to the minus 14 divided by 3.3 times 10 to the minus 6. And I'm not even going to give you an answer. What I want is I want you to actually sub this in and do the work and compare as a class to see the answer that you get. Okay, for any acid or base, you can calculate both H ions and OH ions. What you do is in acids, you first determine the H. So the way you do that depends on if it's a strong acid or if it's a weak acid. Okay, so the strong acid is just you use the balanced equation. A weak acid, you have to balance the equation and then you have to use Ka or Kb. So I'm just going to write there's 3 steps. Then you use Kw to calculate OH. So then you go through this process where you say Kw is equal to H plus OH. You already knew H, so you're solving for this last guy here. Okay, bases is the same thing. First we determine OH, and it depends if you have a strong or a weak. There's 2 different methods. So there should be something in the wording that tells you it's strong or weak. And then you use Kw to calculate H. Some things to think about in water, which is neutral. the concentration is the same of H and OH, which is 1.0 times 10 to the minus 7. In acids, the concentration of H will be greater than that, and OH will be less. In bases, OH will be greater, and H will be less. Okay, there is a practice set of questions. They're called practice set 2. What I would like you to do is I would like you to do questions 1 through 7, okay? And I would like these finished. Today is Tuesday. By Thursday, I would like questions 1 through 7 finished, okay? We are going to start something new um, on Thursday, so I would like this finished by then. Sorry, on Wednesday, we're going to start something new. So this is on your own time. You have the rest of today to do questions 1 through 7. There are some, I give you a mass, and you have to figure out the ion concentration. But you can go mass to moles, and moles per liter is concentration. You guys have all the tools. Get together with someone else who can give you a hand and try these questions 1 through 7. They're practice questions. They're not for marks. But if you don't do them, you're robbing yourself the opportunity to learn this concept.